Hello, Calculus students and seekers of truth. In this video, we are going to study and review a little bit about sequences, series, and in particular, geometric series. And again, this falls into the context within the grand scope of Taylor series, Taylor polynomials, these big concepts, a very big concept in calculus. And what I hope to do here is kind of review some things that you have learned before and then quickly get you up to date and prepared so that we can use this in service of Taylor series, Taylor polynomials, the bigger concepts. Okay. All right. So let's start with some definition. A sequence is just a list of numbers with a discernible pattern. So, for example, if I said 1, 1, 2, 3, 5, 8, 13. Okay. So this is a list of numbers. There is a pattern to this. It might not be necessarily obvious at first, so the pattern may not be simple, but there is a discernible pattern in there somewhere. So this is a sequence. It can go on forever. In fact, this one does go on forever, and so we indicate that with the ellipse. A term is a specific number in a sequence, and it's usually identified by an integer, not just a number, by an integer that's greater than or equal to 0. So for example, if I want to call this series, this sequence here, let's say I want to name it sequence S, okay? Then I can say that S sub 1 is equal to 1. That's the first term in the series, in the sequence. S sub 2 is also equal to 1. S sub 3, that's how we pronounce these little notations, is equal to 2. So that's just saying the first term is 1, the second term is 1, the third term is 2, the fourth term is 3, and so on. Okay. Go one more. And the fifth term is 5. I don't necessarily have to start with S sub 1. Sometimes it's more convenient to start out with 0. So I could also say the 0th term of this sequence is 1. The first term is 1. And so I'm just kind of off by 1 here. That's a perfectly reasonable way to say it. Sometimes we can say like we can have negative indices or negative terms, but that's very, very rare. So this is still the fifth term in the sequence. 5 here is still the fifth term in the sequence, but the index here, or yeah, the term number happens to be 4 because we started counting at 0. You'll see both of these starting at 0, starting at 1. It's really meant for a sake of convenience rather than anything for particularly interesting meaning, right? Now, let's move on to the next topic here, which is a series. So this is a sequence. Now let's talk about a series. And so a series is just the sum of all the terms in a sequence. And a series is actually just a really long way of describing a singular number. Right? So because you think about it, it's just if you add everything up, you're going to get a number. Now, except for the case where if you add everything up and you get like an ever-growing number, an infinitely large number, in which case we just say that the series is divergent. So for example, this is the sequence. To make it a series, we just say 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13, so on, right? And you can see obviously that these terms are getting bigger, and so this series is going to be divergent. Now, in some cases, the series will be convergent. Okay? Now, it's important to make the distinctions between a sequence being divergent or finite and a series being divergent. Those are not necessarily always in lockstep with each other. They don't always, there's not a one-to-one correspondence with them. Okay? So that's what a series is. A partial sum is kind of like a cumulative sum of the terms in a series. In a sequence. Okay, so it's the sum of part of a sequence. So, and the way we typically write partial sums is we write them in a way that's cumulative. So, for example, well, I'm going to use p here to represent. Actually, I'm going to use let's use p here to represent the partial sums. Okay, so the 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 first partial sum of the sequence is just a single term, so that's just 1. Then the second partial sum is 1 plus 1, so that's 2. The third partial sum is 1 plus 1 plus 2, so that gives us 4. Then 1 plus 1 plus 2 plus 3, so that gives us 7. Then you're going to add 5 on top of that, so that gives you 12. And then you're going to get 8 more, so that's going to give you 20. And then 13 more, so that's going to give you 13. And this list is going to go, sorry, what am I saying? 13, 33, not 13. Let's correct that. 33. And the list is going to go on and on. And we can also notice here that partial sums is a sequence itself, right? So the partial sum of a series is itself a sequence. So things here start to get a little bit more interesting. And we can also you can also see sometimes it will be listed this way: P1 equals 1. So the first partial sum is 1. The second partial sum is 2. The third partial sum is 3. Sorry, is 4 of this particular sequence that I started out with. So hopefully that gives you some understanding, some context as to into the world of sequences and series. Okay. Let's go down here. Let's do another example here. This time with the summation symbol. So if you remember when we did Riemann sums, this sigma here, the Greek letter sigma, just means to add it all up. N here is going to be an integer, and it tells us where to start. And then up here, it tells us where to end. So in this case, we're going to start at 1, and then we're going to keep on increasing. And so we're going to list out the sequence first. So first term of the sequence is 1 over 1, so that's just 1. The second term of the sequence is 1 over 2, so that's 1/2. The third term is 1 over 3. The fourth term is 1 over 4. And we're just going to keep on going like this onto infinity. So we can just put plus signs in between all of this. And that tells us that we're going to add up all of these numbers here, all of these fractions. 1 plus 1/2 plus 1/3 plus 1/4, onwards and onwards and onwards. And I just want to make a note here. You can see here that the sequence, the list of numbers here, is getting smaller and smaller and smaller. And so the sequence will converge. Right? You see that the sequence would get each of the individual numbers would get smaller and smaller and smaller to 0. Now, what about the series? Okay, will this sum get eventually approach some value, or is it going to grow into infinity? And this is here where it starts to get interesting, where it's no longer obvious because we're adding on a little bit each time, right? So 1 and then 1.5 and then 1.5 plus 1/3. So that gives you like a bigger number, but it's not growing as fast as it used to grow. So this is where things get to be a little bit more interesting when we start to study a sequence that converges. But the series, I don't know, maybe it converges, maybe it doesn't. All right, so I think it's a good spot to end it here. And in the next videos, we'll pick this up and we'll talk about, well, what's the definition of, what's the rigorous way to determine whether a sequence or a series will converge or not. Thank you for watching and have a wonderful day.